Let's have a look at some of the practical applications of logarithms, and particularly things that are measured in logarithms. In 2011 in New Zealand, there was a magnitude 6.3 earthquake in Christchurch, and it was incredibly destructive. There's still buildings that haven't been rebuilt, and it killed a lot of people. What does that mean, though? What does the 6.3 mean? This year, the strongest earthquake is apparently an 8.8 magnitude earthquake in Siberia. Caused a lot less damage. So let's ask ourselves a question. How much more powerful is an 8.8 magnitude earthquake than a 6.3 magnitude earthquake? First off, we have to understand what a Richter scale actually measures. It measures actually the amplitude of the waves that are measured at a certain distance from the epicenter, that is where the earthquake occurred first in the Earth's crust. Although it's kind of directly proportional to the amount of energy that's released. The magnitude is log 10 of the strength of the quake over a reference quake. And a reference quake is a magnitude 1 quake, which is the smallest possible quake that can be measured. So when we compare them, the reference quake is going to be the same, and it's going to be essentially equal to 1. So we can ignore that for now. So we want to know how much energy is going to be released from each earthquake. Well, let's work it out. So the Christchurch earthquake was 6.3. So that means 6.3 equals log 10, and because it's going to be that reference is going to cancel, it's going to be the strength of Christchurch. I'm going to put it like that. Excuse my terrible handwriting there. So let's get rid of this base 10 business. So I'm going to make both of them equal to the power of 10. And these two are going to cancel. So the strength of the Christchurch earthquake is going to be equal to 10.63, and we'll say, megajoules or something of energy. But it's just 10 to the power of 6.3, which is going to be, get out. So 10 to the power of 6.3. Let's just say that it's equal to 1.9. So 19.262. Okay, and the strength of the Siberian earthquake is going to be 10 to the power of 8.8. 10 to the power of 8.8 is that. A huge number. Which is 630,957,344. course, you're going to do it to significant figures. So how many times more powerful was the Siberian earthquake from the Christchurch earthquake? Well, let's just divide that by the last answer. So 1995, 262, 316 times more powerful. So the question must be asked then, why was the Christchurch earthquake so much more destructive than the Siberian earthquake? And the answer is there's three big answers. The first one is that Christchurch really wasn't so much of an earthquake prone place. So they hadn't really thought that there was a magnitude of that size earthquake coming. So a lot more of the buildings were built in stone and were not as earthquake reinforced as they would be in places like Nelson or Wellington or the Hawke's Bay, which do have a lot of earthquakes. The second reason is, let's just look at the scale of where the epicenter was. This is the epicenter here of the Siberian earthquake, and there's no inhabited places anywhere near it. Japan is all the way over here. This is Siberia. There is a village, a town that's there, but it's 175 kilometers away. It's also at a bigger depth. This was at 30 kilometers into the Earth's crust. This is the Christchurch earthquake. This is the epicenter here, and this is Christchurch. I mean, it's essentially right on top of Christchurch. It's kind of within the metropolitan area of Christchurch, but also it was incredibly shallow. It was at 5 kilometers, which is almost nothing in terms of earthquakes below the city. So you have a big earthquake happening pretty much right underneath the city that's not really used to having earthquakes. There's going to be an enormous amount of destruction and life lost, and that's what happened, unfortunately. Okay, another example of logarithms being used, or logarithmic scale really being used, is in sound. So you're probably all familiar with a decibel. But what does a decibel actually mean? Well, the deci kind of means 10, and bell kind of is a bit like a ringing bell, I guess. It's a logarithmic scale, and what I've got here is a mashup of the two things that I want to compare in this case. In 1976, the British rock group The Who, in a concert, were measured at 129 decibels, which at the time was a world record for volume. They were famous for being loud. Pete Townsend, the guitarist for The Who, famously suffers from bad hearing, and it's not really a surprise. So 129 decibels. Let's compare that to a 747 taking off, and that's 102 to 103 decibels. So you could be thinking, well, The Who is 27 decibels louder than 747. Not quite. A decibel is 10 times log 10 of the sound intensity over something which is barely audible, and it's a reference, and like the earthquake, it's going to be essentially equal to 1. Okay, so we can ignore it when we talk about it. The decibel comes from this 10 here, by the way. Deci meaning 10. So how much more loud was the Who than a 747 taking off? Well, let's work it out. So the Who were 129, 10 times log, and because that's one, we can let's ignore it, of the sound intensity, the volume. So let's divide both sides by 10, so 12.9 equals log of the sound intensity. So the sound intensity, the volume of the Who, was 10 to the power of 12.9. All right, which is an enormous number. It's going to be one in front of almost 13 zeros. Huge number. And the jumbo jet is also going to be a pretty big number as well. But let's work it out. So that's going to be the 747. It's going to be, let's say 103 divided by 10 is 10.3. So it's the sound intensity of the 747 is going to be equal to 10 to the power of 10.3, a lot, but nowhere near as loud as the Who. Let's grab our calculators. So let's work out how much much more louder the Who is than a 747. So 10 to the power of 12.9 is that. Wow. Divide that by 10 to the power of 10.3. So they're 398 times louder, more sound intensity than a 747. I mean, I love the Who, but wow, that's dangerously loud. And there are other bands that claim to be louder. They say they got it to 147 decibels. I doubt that. It's dangerously loud. Wow, that is loud. Gee. The third scale that we're going to look at is the pH scale. pH scale is kind of in modern vernacular and the popular vernacular as sort of a measure of acidity. How acidic something is, or how acidic, or how base. Ooh, how base something is, alkali something is. So it's generally accepted that a pH between 1 and 3 is a strong acid, and 7 is water. So in between there, say about 5 to 6 is a weak acid, and anywhere from 11 to 13 is a base, and anything above 13 is a really, really strong base. What does that mean though? Well, it means a strong acid isn't really necessarily how strong an acid is. It's actually how much it dissociates in water. So it's related to how strong it is, but really it's into its pH, but really it's a dissociation. It's a measure. So the pH is defined as the negative log base 10 of the concentration of hydrogen ions. So that's ions that are missing an electron. This is the stuff that makes acid, essentially. All right, let's compare how acidic two things are. So these things are both acidic. Let's look at hydrochloric acid, HCl, and that's got a pH. Sorry, it has to be P capital H. The H is hydrogen here, and that's got a pH of around about, looked it up, didn't I? Around about 0.8. That's pretty nasty. You want to be taking portions of that. You definitely don't want to be getting that on your hands, on your clothes, and you'll be wearing goggles for your handling that. You definitely do not want that anywhere near your eyes. I've been in a lab where someone's got something nasty like that splashed in their eyes, and it's not pleasant. Like, I can tell you that for nothing. With the pH, let's compare that to a weaker acid, kind of weak, and speech marks there in quotes, and that's the pH of coffee. Say black coffee, and I looked it up, and it has a pH of around about 4.7. So the square brackets there is not the amount of hydrogen ions, it's the concentration of hydrogen ions. So how many ions there are to a certain amount of something. Okay, so what's the different concentration in pH of hydrochloric acid, HCl, and coffee? Let's work it out. So the concentration of hydrogen in HCl, well, let's work it out. We've got 0.8 is equal to negative log of that. And that's what we're trying to work out. Let's multiply both sides by -1. So negative 0.8 equals log base 10 of that. So that means that the concentration of this is going to be 10 to the power of negative 0.8. In the power of negative 0.8. So 0.16, 0.158. Okay, fair enough. Now let's look at the concentration of coffee. So the concentration of coffee is 4.7. So that means that 4.7 equals the negative log base 10 of the concentration of hydrogen. So minus 4.7 equals log 10 of that concentration. So that means that the concentration, that is how acidic the coffee is going to be 10 to the power of negative 4.7. 10 to the power of negative 4.7, and that's going to be a tiny number times 10 to the power of -1. Okay, that's going to be 0.000001995. Well, there's a big difference between this number here and this number here. Let's actually work it out. Let's divide that by 10 to the power of negative 0.8. That, then take the inverse. So that tells us that hydrochloric acid the concentration of hydrogen ions is 7,943 times greater. A lot. So with hydrochloric acid, you want to avoid it at all costs. That you wouldn't even make it until you really needed to use it. Whereas coffee, you can guzzle it all day, and I know that I do. Okay. Next one. Let's say that your gran gives you $1,000 and tells you to invest it in the bank. Invest in the bank until you get $1,500 in the bank, and you invest it at 5%. How many years do you need to wait? It compounds once per year. Well, we know that the value of the amount is going to be equal to the, at any time, is going to be equal to the initial value, which is going to be 1,000, times 1 plus the rate to the power of the time it took to get there. Well, we know that VO is 1,000. We know that V that we're looking for is V5, and that's 1,500. And we know that time is not known, and the rate is 5%, which is 0.05 as a decimal. So now we can solve that. So 1,500 is going to be equal to 1,000 times 1.05, the power of t. We need to solve that t. Well, let's go as long as we can without needing to work that out. So let's divide both sides by 1,000. So that's going to be 1.5 equals 1.05 to the power of t. Now I want to bring that t there. If only there was something that could help us do that. Let's just take a log of both sides. So log base 10 is fine. In this case, it's going to be equal to log of 1.05, the power of t. But remember, when we take the log of something, the exponent can come out the front, which is t times log of 1.05. So if we divide both sides by log of 1.05, we're going to find t. So t is going to equal to log of 1.5 divided by log of 1.05. And just remember that that is not equal to log of 1.5 over 1.05. It's not equal to that. We put that in our calculator, we can work that out. So log of 1.5 divided by log of 1.05, 8.3 years. So sometime during the 9th year, we're going to have $1,500. So that's presuming that the bank doesn't take any bank charges off us, or there's no monkey business. And those are practical uses of logarithms.